Welcome back, folks. Here's the first in a series of videos that I think gets to the heart of the matter as to why complex numbers are important. All of the operations that you learn to do in grade school, add, subtract, multiply, divide, all of those operations that you did in one dimension, we're really doing the same stuff. We're doing the same stuff, but we're doing it in two dimensions. Some of this takes kind of a reconfiguration of how we think about these operations. And there's some kind of like intermediate operations that happen in there as well. But the important thing is, if we can add numbers in one dimension, we can add numbers in two dimensions. And if we can subtract, we can do it in both, in one dimension and two dimensions. Same with multiplication, same with division. That's what's important about complex numbers. Square root of -1, it's true. I'll do a video on the fact that it's true, but it all comes out of the fact that these operations are the same. Okay, so before we dive into our first one, which is going to be addition, if you're stuck on a desert island and you're having to work with complex numbers, I don't know why you would do that, but it's going to be easier to do some operations in some forms and some operations in others. So if I'm adding or subtracting and then negation, right, just taking the negative of the number, I can do that in rectangular pretty easily. If I'm multiplying or dividing or negating, I can also, oh, hey, look, that one's on both sides. Okay. Or inverting a number, so that's doing 1 over that number. I find that's much easier in polar. Okay, so the conversion back and forth, might be necessary to do these operations. More often than not, I'm having a calculator do this. I'm having a computer do this. But understanding the basics of why complex numbers are important and kind of how to work with them is equally important, so that you have some conceptual idea of what you're doing, so you're not just plugging numbers into a computer and hoping they come out right. Okay, so the first one I want to look at is addition. So let's start with addition. Okay, get the colored pen I want. Okay, and a lot of this feels like we're going back to kindergarten. You might have a word problem, and that word problem might require you to represent how far somebody has walked in a direction, right? You might say, Colin walks 2 meters in one direction. Okay. Then he starts again and he walks 3 meters in the same direction. How far is Colin from where he started, right? So in that instance, the number's representing just literal distance. Okay. And we can represent that as distance from the origin. We might restate that and have it represent a quantity. We might say Lauren has 2 apples and Anna gave her 3 apples, right? How many apples does Lauren have? Like, this is going back to grade school, like really early grade school. And we use that point in space to represent how many apples Lauren has. It's all the same stuff, okay? We're going to use it to represent voltages. We're going to write a KVL, and we're going to say how much voltage did we go up across an element? How much voltage did we go up the next element? Okay, so it really doesn't matter. But if we're going to do that on a number line in one dimension, okay, it might look like this. Okay, we might say, it looks like I have meters here, so this is Colin walking. So he starts off and he goes in one direction and he walks for 2 meters. Okay, and that 2 meters is represented by that blue vector. Okay, now we take a vector that's 3 meters. Okay, if I move that and I start it back at the origin, it would end up here. But we're not. We're starting at 2 instead of at 0. And we continue on for another 3 meters in the same direction. And we get out here to 5. Okay, so we could represent his final location just as a single vector. And we would get 5. Okay, 5 meters from the origin, and we went right in both cases. So you did these kinds of problems in grade school, I have no doubt. And what you didn't know is that you were doing complex arithmetic. The only problem was you were constrained to the number line, to the real axis, okay, in this case. and we never moved off up or down in this on the complex plane. So you might have written it out this way. Let's see, it looks like this, right? You might have said 2 plus 3 equals 5. Okay, I went old school and I stacked them up like you did in grade school. And the reality was you just had plus J0 on each of those. Okay, graphically what we're doing when we do something like this, and when I think of addition, I say, let's see, what color do I want this in? Put vectors tip to tail. Tip to tail. Okay, so I took that 3 and I moved the tail of it out to the tip of the previous one. And then I saw where that landed me. Okay, so we're putting vectors tip to tail graphically. All right, so if we wanted to do this in 2 dimensions, okay, let's say, do I have this one already typed up nice and pretty? Oh yeah, let's do this one. Ready? Look at that. Put the vectors tip to tail. Okay, so in 2 dimensions, here's an example. So separate numbers. 4 plus J3 plus -2 plus J1. Okay, we can line these up, and this is why it's easy to do in rectangular, because we just say 4 plus -2, well, that's 2. And we say 3 plus 1 is 4, so 4. So we get 2 plus J4. Graphically, what's going on is we're sticking these values tip to tail. Okay, so let me grab this graphic and put it down here like this. Okay, we're putting the vectors tip to tail. Here's 4 plus J3 in blue. Okay, and -2 plus J1 in red. Okay, notice how those are tip to tail. And then the result is the vector that points from the origin to the tip of that second one. 2 plus J4. Okay, and that's all we're doing with addition. Now it's much easier in rectangular. Okay, if you wanted to do these in polar, okay, it would look something like this. Okay, so I'll just say much harder in polar. All right, I'm not going to look at this and be able to do that in my head. I stand a shot of doing this one in my head. All right, so that's why I prefer using rectangular form when I'm working with addition. Okay, so that's the first operation that we got to deal with. If we want to get to subtraction, we got to take a little detour and we got to go through negation. Okay, so the next video is going to be hopefully short and sweet like this one, and we'll deal with negating numbers. How do we do 4 and then take the negative of maybe get to -4? Okay, how do we do that in 2 dimensions? All right, stay tuned and good luck.